Welcome, everybody, to the session after the lunch. Hope you all are well. Thanks for coming. My name is Hudalla from Bosch IO. I have been working in IoT projects and recently started working in the automotive environment in the software-defined vehicle working group. And today I want to tell you about the fleet management blueprint that we have created within the SDV working group in order to illustrate some maybe useful application of the technology that we create there. I have been asked to show this slide as well, so after the session you can rate what I have said, whether that was useful or not. But I would like to start with a very short introduction of the software-defined vehicle working group. This is a group of OEMs and tiers in the automotive sector who have gathered together in a working group to try to develop some technology that can be shared in the software-defined vehicle domain. A lot of this technology is at the infrastructure level or is implementing some very specific functionality, which makes it kind of hard for outstanders to understand what it is good for or what you can actually do with it. The landscape at the bottom illustrates this a little. The different projects all fit into one of these categories, but each and one of them considered individually might not really give you a good impression of what role it might play in a real-world application. So what we did then is started to create the SDV Blueprints project, which is a collection of example use cases that we want to use to showcase the technology so that people who are not that deep into the technology yet can get a better feeling for what can the technology be used, what is its purpose in this overall picture, and by using a use case that is more approachable for people or that is more illustrative, we hope that we can attract more people for the technology. So one of these blueprints is the fleet management blueprint, and that is what I want to talk about. So the fleet management use case is about managing fleets of commercial vehicles. And commercial vehicles are usually something like trucks or delivery vans, rental cars, but also construction machines like truck front loaders or something like that. These fleets often are limited in number as compared to the passenger car domain. So we are usually talking about hundreds to thousands of vehicles in these fleets. And these fleets are usually owned by companies that make a business out of it. So why would they do that? Why do they need to manage these fleets of commercial vehicles? And this slide I have stolen from the Covisa meeting that has been taken place recently, where they have started to also think about commercial vehicles in general, and they identified several of these clusters here of functionality that might be of interest when managing fleets of vehicles. And below you can see some of the benefits that people want to gain out of it. So for example, you want to usually increase the lifetime of the vehicles by reducing maintenance or predicting when maintenance will be due. You want to know how much fuel your fleet consumes, what the mileage of the vehicles is, and stuff like that. So today's fleet management world looks mostly like this. You have different fleet management service providers, which often provide their services as a cloud service. And then in order to use the service, you need to onboard your fleet. And that usually entails that you put a piece of hardware, a telematics control unit, into your vehicle, into your truck, attach it to the CAN bus somehow, maybe via the onboard diagnosis plug, and then the TCU runs a piece of dedicated software that collects the data in the vehicle and sends it back to the fleet management service provider's backend in the cloud. All of this is completely proprietary usually. So the fleet management service is proprietary, the black box, the TCU, is proprietary, and the software is proprietary. This works, but it also means that the fleet management service providers need to maintain, build, and give away this hardware, often for free or for a small fee. And they need to create or build this software or have it developed for them. And all of that is only necessary in order to get the data into their service, which is what they actually need. So they have no real interest in selling this hardware because for them this is just a necessity. For the customers of these fleet management services, it means that once you have equipped all of your vehicles with this hardware, you can use the backend service of fleet management service provider A, but if you want to switch the provider, you need to do the same thing all over again with a different piece of hardware. So this is also very costly. So all in all, this being a totally proprietary thing where nobody actually gives a damn about what the hardware and software is that runs in the vehicle, this sounded like a very good example for the value of open source, because the thing on the left-hand side, the hardware and the software running there, is not a differentiating thing for the fleet management service providers. They need it in order to get to the data, but they don't really care where it comes from or how it is built. So this in itself is a good opportunity for the software-defined vehicle work group to step in and make the situation a little better. So you could, for example, imagine that there is an implementation of a TCU that runs a software-defined vehicle software stack as we develop it in the working group, which provides means to uniquely or uniformly provide access to the CAN bus, to the data, and which also provides a means of deploying software to it remotely. And all of a sudden, the picture changes, and now the only proprietary thing is the telemetry adapter software that is specific to the FMS provider. So this is a first step in the right direction from our point of view. You could, however, improve the overall situation a little more by trying to adopt and leverage standards in the field. So there is a very widely known standard called SAE J1939, which, does anybody know that standard? Okay, it's not too many, so I'll spend a few words on it. So it basically defines standard messages and data encoding for information on the CAN bus. In general, the CAN bus messages are very specific and proprietary to the OEMs, but in the commercial vehicle domain, there is an industry consortium, the SAE, who has standardized these messages and some of the data, so you actually know what to expect and what to read from the CAN bus in order to get to the data like current speed, engine speed, fuel consumption, stuff like that. So what you can then, however, do, or what we advise you to do, is not operate directly on the raw CAN bus data, but instead try to use a so-called vehicle abstraction. And this vehicle abstraction layer has been defined by the COVISA. It's called the Vehicle Signal Specification. And what it does is it provides a tree of signals that reflect or represent the properties or the current state of the vehicle. So you could take a look at the current speed, the fuel type. You get the idea. So it defines a standard naming for all of these properties and defines how the data is encoded and how it is to be interpreted. Using this way, you can now implement a generic telemetry adapter which operates on top of this tree in order to retrieve all the data that is relevant for doing the fleet management. And the generic telemetry adapter can now transmit this data into the backend, where you could also have a generic telemetry gateway which stores this data into a generic database, for example, a time series database. And then the fleet management service providers could access that data and retrieve the data using standard APIs. And here are two examples of these APIs. To the right-hand side, it's the VIS2 API that has been standardized within the W3C. And the FMS standard is a standard developed by a European consortium of commercial vehicle OEMs. And both define an HTTP-based or even RESTful API to query and retrieve the data that is available in the database. So using this approach, all of a sudden, the whole picture totally changes, because now the fleet management service providers do no longer need to create these proprietary boxes and software, but instead could use generic software that is always the same, regardless of where you want to deploy it. And one of the ultimate goal for this architecture would then, of course, be that the vehicle OEMs actually start providing a runtime environment within their vehicle when it gets out of the factory, so that you do not need to retrofit anything at all, but instead, in their high-performance computer in their vehicle, they already provide an SDV-conformant runtime environment where you can simply deploy this generic piece of software, and that is what you need to do in order to integrate your vehicle into such a fleet management environment. So what we did in the blueprint is we created a simple setup of some service components. Some of them run in the vehicle and some run in the backend, in the cloud. And this is the standard simple setup that we use in order to showcase it when you want to run it on your laptop only. So what we have is we have a data broker component down there. The data broker provides the vehicle abstraction by means of this VSS tree. And then we have this FMS forwarder component, which plays the role of this generic telemetry adapter. And it periodically retrieves the data from the data broker using the VSS-based signal API. It then writes this data into an influx time series database in the backend. And from there, you can create a generic a Grafana dashboard to visualize the data, or you can use the FMS server component to retrieve the data using the FMS API. So this is the standard setup that we use on a laptop, but we also have a variant that is a little more advanced, where we do not have this direct connection between the FMS forwarder and the InfluxDB, which is a little inconvenient that you tie the vehicle to the database implementation. That is usually not what you want to do. But instead, in this case, we use a messaging indirection in between. And in this case, the FMS forwarder connects to Eclipse Hono, which is another project that I'm working on, which provides a device connectivity layer. And it uses MQTT to transmit messages that contain the FMS data. It transmits that to Hono, and Hono exposes this data via Apache Kafka to consume the data. And that is what the FMS consumer does. It reads the data from this Kafka topics, decodes the data, and inserts it into the InfluxDB database, but the rest of the setup is the same then. So this is what I also want to show you. And I actually have a bet running with one of my colleagues whether the demo will now work. Yesterday evening it hasn't, but when I started setting it up here, it looked pretty good. So let's pray to the demo gods and see whether this actually works. So this is a console on this Raspberry Pi here that I have. It's a Raspberry Pi 4. And we have flashed it with a LiDAR image. That is Eclipse LiDAR, which is a Yocto-based distribution of the Linux kernel, along with some software components provided by the EclipseCon project, as you could have seen on the previous slides. And these components are used to run some container workloads, and that is exactly what we are doing here. So the three components that you have seen on the slide are the ones up here. These are 3 Docker containers, and for example, the interesting one, the FMS forwarder, is periodically pulling the data from the data broker and forwarding it via MQTT to the Eclipse Hono sandbox on the internet. So what we then have in the back end is the counterpart, which is a set of containers that implement the other components. So we have the FMS consumer, and we have a Grafana server running, and the FMS server, the InfluxDB. And what we can, for example, now also see is the logs of the FMS consumer, how it actually receives the data from the Kafka topic, decodes the data, and writes it into the InfluxDB. And finally, what you can then also hopefully see is the data flowing into the Grafana dashboard here. So this is the live data that is coming from the Raspberry Pi. It's a selection of the telemetry data, like speed, engine speed, fuel levels, you name it, ambient air temperature. Below there, you see something that is usually important in commercial vehicles, in trucks. This is the driver status, for example. A driver can actually work or drive the vehicle, or it can rest, and this illustrates the different status that it's in. And there are certain regulations that a driver has to rest for, I don't know, half an hour after 3 working hours or stuff like that. So this is what you get. This is just for illustration purposes, but a real fleet management service application would, of course, have a much finer-grained selection of data and many more data points that they consider when they work on that. So let's see if we go back. So by the way, my colleague now has won a whiskey sour at the bar tonight at the Nestor, if you want to join us. So, okay. So what is next in this area? The setup has been very simple so far, and what we soon learned in conversations with real fleet management service providers like Geotab is that they need data in a different quality. They need more data usually, and they need more specific data. And they also often face the question, how often do we need to transmit this data? Because there's a cost with that, of course. If you sample the data at, say, 10 hertz, then you are creating a lot of data, and you need to transmit that over public infrastructure, which comes at a cost. And most of the time, the data is not really important to sample at this frequency, because it doesn't really make a difference if you sample the fuel level every 30 seconds or every 5 minutes, because within 5 minutes, the fuel level does not really fall significantly. But there are use cases where it is actually very important, and one of those is, for example, to detect what a vehicle actually does, how it drives. So, for example, if you sample the GPS location of the vehicle every 30 seconds, then you can end up in a situation which is illustrated by the orange track, meaning the vehicle that you are monitoring ends up on the other lane. And you might now be worried, hey, what happened there? Did he break through the barrier in the middle and is now driving on the wrong lane? When in reality, he has made a U-turn. But you only would realize that if you were sampling the data not only every 30 seconds, but continuously. Now, the question is, how can you actually still realize what is actually happening without having to sample the data every 10 milliseconds? And one of the solutions to that problem is a thing called the curve logic sampling that Geotab has created, and that provides a way to continuously sample the data at a high frequency locally in the vehicle, but then filter out cleverly all of the redundant and unnecessary data and only keep those data points that actually make a difference or that are worth being notified. And they also have created an implementation of that in Python. And we have created an issue where we are talking about integrating that into the fleet management use case now. And that is what we will do together with Geotab. So another step that we are thinking about is, how does the software actually get into the vehicle? So in the setup that I've shown you, I basically did everything manually. I opened a remote shell to get into the vehicle, to copy some configuration there, some data, started the containers there. But Eclipse LEDA, and in particular the Eclipse Canto project, also provides means to remotely deploy software on the vehicle. So how this works is the vehicle is connected to an uplink in the cloud where it can receive commands. And one of those commands, for example, is a thing called a desired state. It defines a set of components, of software components that you want the vehicle to run. And publishing or pushing this information to the Canto Update Manager component then would result in these container images to be pulled from the internet and being started locally, so that I would no longer have to log into the vehicle remotely, but I could simply roll out all of these components using this mechanism. So this is something that comes with the next release of Eclipse Canto. I'm getting a broad smile because that is coming up next, and that is what we want to incorporate here as well. And this is a list of resources of all of the topics and things that I have talked about. So this is just for your reference. But with this, I'm already at the end. Thank you very much for your patience.